Good evening, everyone. Welcome to SF Scala Meetup and Vancouver Scala Meetup tonight. Thank you all for coming. Tonight's speaker is Adam Rosien of Inner Product. He's going to be talking about essential effects. Over to you, Adam.
Hi, thanks for having me. It's been a long time since I've given a talk because of the world, but I'm very happy to do so. So my name's Adam Rosien, and I work for a small company called Inner Product. I started out, well, not really, but back in the day, I worked with Underscore, who you might know, and that's where I met Noel Welsh, and I kind of was the U.S. version, the U.S. associate over here for Underscore, which is mainly some EU folks. And then we decided to make our own little consulting company here. So we do a lot of things like we do a lot of training, we do mentoring. So if you want a nerd as a service, you just sign up with us, and we can help you fix bugs, develop your product, work in your staff, work along with your staff on projects. And kind of what I've been spending a fair amount of time with lately has been a new course and a book called Essential Effects. So it's about how do we, well, I'm gonna share basically what it's all about. You might have heard about effects through things like side effects. I'm gonna kind of assume that folks are somewhat exposed to effects and like Katz's effect, but I'm not really gonna assume that people know too much. So it's not gonna be a very advanced talk. I'm happy to sort of stay on, and there's other folks online who could answer some of the fancier questions. I'm happy to talk about that after the main talk. But this is meant to introduce effects, why we should care about them, what do we need to know, and how to use Katz's effect to take advantage of some of these patterns. So the big news right now that I was furiously working on minutes before I actually arrived here is that the book I just published the sort of early access edition. So you can go to essentialeffects.dev and you can buy it for the early access price. It has everything that I've been talking about. There's a bunch of exercise. It's 170 some pages. I was really nervous to sort of put it out because you're like, oh, there's going to be some stupid mistake that I'm going to get embarrassed about. But you got to just sort of push the button. And having this talk was a good deadline to sort of force myself to do it. So please check that out. Let me know what you think. So here's kind of what I'm hoping to talk about today. I should probably get to all of it. It's not going to cover everything in Katz's effect, but I tried to sort of figure out a good subset to be able to cover in maybe about 45 minutes worth of time in order to have some questions. There's lots of other aspects, but these are the big parts. And so as Solaris mentioned, please let me know if you have any questions or if you need me to repeat something or I say something wrong or something like that. He'll prompt me. I don't know if I can see you directly. So that's what we're going to do. We're going to start there. It is difficult to give a talk when I can't quite see your faces. So if I say a bad joke, I'm going to laugh. So you don't have to. All right, there we go. See, I can hear it. I can hear the laughing. All right, so we're going to talk first about effects. And this is going to be a bit more about like, what's the point of all these things? Why do we care? And since we're functional programmers, or we pretend to be, or we get paid to be functional programmers, we always have to talk about the substitution model of evaluation. So this is a model of evaluation. This is not what really happens in the computer, but it's a way for us humans to understand it. And sort of the typical way we teach it and talk about it is we have some sort of expression. We usually use arithmetic. And we have some expression like 3 times 4 plus 2 times 5. This is an expression, and we assign it to a value. And the basic idea is that we have these expressions, and oh wait, expressions are made up of others. So please, internet gods, treat me well. we have this model of evaluation where we have these expressions, and they, they're made up of other expressions, and then we evaluate them. So we simplify the first one, the first sub-expression, 3 times 4, that's 12, and we say, oh, there's another sub-expression, 2 times 5, that's 10, and we have yet another expression. So there's a very mechanical process. And we get an answer that is no longer an expression, but it's a value. It's a value that we can no longer evaluate again. So this is a very simple model. It's not exactly what really happens in the computer, but it's for us as humans to sort of be able to explain to ourselves something that the computer should match. The computer should get the same answer. We can teach people how to do this. It's a very, we teach them the rules, how to, start on the innermost expressions, or there's some rules around it. And it's so easy, even a computer can do it. So this is nice, but unfortunately, a lot of what we do doesn't follow this model. So when does substitution not work? When does it break down? So have a little think, have a slurp of tea. When does substitution not work? I'll give you some examples. You probably have seen this before. So one example would be the sort of ubiquitous print line method, and that'll print something to the console. If we evaluate that expression, it has type unit, so it returns a unit. And so when we're performing the substitution, we should be able to substitute the expression for what it evaluates. When we say that one thing is substitutable for another, it means that they mean the same thing. But does printing to the console mean the same thing as unit? No, because if we just had a unit, there's no printing going on. So this is where sort of the term side effects comes into place. There's some sort of side effect that we're declaring is embedded in the meaning of print line, but we can't really see it because when we evaluate it, all we get is this unit out, and unit does not mean the same thing as printing to the console. Other examples would be instead of writing sort of to the outside world, maybe we're reading something from the environment, from the outside world. I might be reading a line from the console, or I might be even, you can think about it as, reading some bytes from a file. You don't know what's in the file. And so if you evaluate something that is interacting with the environment, it will evaluate to whatever's in the file, whatever you typed on the console. But you could have typed something else. You could be reading a different block. So the meaning of this expression here, like read line, is context sensitive. It depends on the state of the outside world. So you can't use substitution to understand what this function is going to do, because you're always going to get something different, or you will likely get something different. And similarly, that carries on to the idea of some, mutable value. So if we're interacting with the environment, if sort of this var is out there, accessible to our expressions that we're programming with, that mutable variable can change. So if I use substitution to evaluate the expression, what it evaluates to really depends on the current state. But as we all know, the current state could change, the environment can change. And so substitution just does not work. And you can think of more and more examples. So why is this important? If we have this world of arithmetic and perhaps other things where the meaning of some expression is maintained when we evaluate it, if they mean the same things as what they do evaluate to, and then we have this other sort of set of things that break that property, where if we perform substitution, they don't mean the same things. How do we deal with that? Well, here's another example that's perhaps a bit more realistic. So this is the future type from the main Scala library. If we had a function, if we had a future, that just printed to the console again, so we can sort of say, aha, I know something sneaky's going on. Well, if we call it twice, we could implement that twice as, do print, and then flat map says, okay, well, after I'm done, perform the action of another feature. If I use the same feature, when I run this, I get the output hello world. If we unpack this a bit, if we perform this substitution process, and I'm going to sort of walk you through it, we can see sort of what might be strange about how feature acts. So substitution is all about substituting expressions for their definitions. So if I substitute print for its definition here, I get that. And then if I do it again, I substitute the print for its definition here. If substitution holds, then this new piece of code should mean the same thing as the original piece of code. And if I then run that thing, so here's my substituted expression. If I run that in your own mental simulator, you're like, what is this? What effect does this have? Well, it prints hello world twice. So there's obviously some difference between what feature the first expression and the second expression that breaks substitution. So here's a nice little picture from our internet friend ImpurPix. There's something going on with feature. Well, so the problem is that these side effects, they happen too soon. So how do we fix things that happen too soon? We don't make them happen too soon. This is easy. Aha. You go to the doctor, it says, oh, my arm hurts. They say, well, don't move your arm. That is the way of functional programmers. We do the exact same thing. Don't want side effects to happen? Don't do side effects now. So if we instead of having future, which has this problem of running things too early, we could sort of create our own, I'm going to call it my IO, just to distinguish it from sort of the real IO, which is a little bit fancier. The idea here is that we're going to capture whatever the effect is, whatever the side effect is, I should say. We're going to capture it in a function. So we're not going to perform the print line or whatever we're going to do now. We're just going to capture it in a zero arg function. And it will eventually produce an A, but just not now. So this is the thing that's actually going to encapsulate our side effect. So we're going to kind of wrap it in this nice little bubble. It's called unsafe because it's meant to sort of give you a warning as a programmer. If somebody calls unsafe, that implies that substitution does not hold. And the idea is that we're going to, isolate this unsafe thing. And everything that we're going to do, any other kind of method that doesn't have this unsafe keyword, we're going to say, oh, well, that's safe, so it will respect substitution. So once we can construct one of these IOs and delay the actual side effect, well, we could just call unsafe run again. That would run it. But we don't want to do that all the time. If we wanted to perhaps transform the output of our IO into a different output, that would be a map call. So we can produce from a my IO A, we can produce a my IO B if we give it an A to B function. And so we could just construct it. We construct a new my IO, and when it's run, so this is the unsafe run, the body of the unsafe run for the new IO. We first run the original unsafe run, and then we transform it with our A to B function. So we're still not running anything. We're just constructing a new my IO. Nothing happens when we call map. And similarly for flat map, we can construct a new my IO that when it's run, not now, but later, we first run the original, we get an A, we call F on A, that gives us a my IO of B. We're supposed to return a B, so we call unsafe run on that thing. So this is where you can see the sequencing happening. First, I run my first effect, that produces a new effect, and then I run the next effect. So this is a little safe container. Inside this container is the unsafe code that doesn't respect substitution. But once we wrap it in it, we can do maps and flat maps, and everything becomes safe. So sort of our checklist, we want to make sure that we're not doing side effects now. We want to do our side effects later. So are we calling unsafe run in the constructor? No, we're capturing some effect here. Are we calling unsafe run during composition? So during maps and flat maps and other methods? No, we're always constructing a new myIO. So this means that substitution can be maintained. So if we take that sort of twice program, and instead of using future, we use myIO, we would construct our myIO, we perform our flat map and do it twice. Now at this point, nothing happens. This is good. This is like, okay, I'm just describing what I want to do. I'm not actually doing it yet. And then you have to explicitly say, go. You have to explicitly say, I'm going to do my unsafe thing that doesn't support substitution anymore, but that's okay. I've constructed my program and I don't need to do anything else now. Now I'm ready to go. If I perform sort of the manual substitution, I replace the expression with its definition. If I do that here and I expand this into its definition, I get this flat map of the two myIOs. If I expand the flat map, here's the definition. You just sort of mechanically the flat map turns into, I'm going to do this thing first. I'm going to do my print line first. I'm going to call F. It produces a new IO. I call unsafe run. And eventually, everything just unwinds. I do my first print line. I then call unsafe run. On the second one, I get an IO out. I print that one, and I get 2 hello worlds, which is what we'd expect.
We do have a question, Adam, if it's a good time for me to interrupt you.
Sure, definitely.
What are the performance implications of effects? Are the thunks stored in the heap? Is there a major trade-off because of this?
I see Daniel's video went on. So there's lots of ways to answer that. I think a safe general answer would be that it usually doesn't matter based on what you're doing. So there's sort of one of the usual arguments is that, oh, well, a lot of what we do in our programs is sort of IO bound. We're talking over the network, or parsing JSON, or I don't know what, but we're not really, the cost of doing these flat maps is not too much. That obviously has a giant asterisk next to it that, of course, it's not the same as just inline functions and sort of normal optimizations. But I can safely say that it gets pretty close. There's certainly different pathologies that you have to know about, and I will probably refer people to chat with somebody like Daniel or Mike after the talk. In general, it's not that big of a deal. And the JVM is really good. So there you go. Thanks for the question. So why am I going through this very tedious exercise? So like we have the substitution and look, we're substituting and everything works out. The reason that this is really important, so here's the magic. Here's a big summary that I'm not quite going to read, but the important part really is that I would say it's sort of part of this first point. The reason substitution is important, and I didn't mention this sort of the word that other people, or not other people, but the words that is often used is referential transparency. What I'm talking about is referential transparency, when substitution holds. So referential transparency, substitution, is a great property to have because it means you can always perform, you can replace some expression with its definition. And if you do that, nothing will change. The behavior that you see will remain unchanged. So it means that you can always do an inline. You can expand a definition with its implementation. You could literally take the code and replace it yourself, and nothing should change in your program. And also the opposite. You're always able to refactor. So if you have some sort of sub-step in a program or in a method, you can always factor that out into its own method, and nothing will have changed. That's a really great property. If you think about some of the hairy code that you might have encountered or even wrote, you might think of examples where you could not do that. If you pulled out some piece and factored it out into another method, it won't work because you're referring to some state or something outside of the lexical scope, and then you have to pass it in, and sort of you're relying on all these things. But if you have this notion of referential transparency, of allowing substitution, you really don't have to worry about those things. And it really helps, it sort of reduces your cognitive burden a lot as a programmer. So that's why this is really important. So that's kind of the basic of effects. We want to make sure that we're not doing these side effects, because if we do side effects now, we can't maintain substitution. And substitution gives us all these other great things. So instead of doing these side effects now, we do them later. And so we end up with something where we can compose our programs. So we can do maps, flat maps, applicative map ends. And we can compose these things, and and all of those operations don't run anything yet. We're just building up a larger and larger program. Then finally, when we're done composing, then we call this unsafe run. And maybe even we do it, as late as possible, which means like in main, when the program starts. That's sort of the best place. So then oh, I've composed my program together, and now go. So that's the idea of effects. Now I'm going to jump into the real I/O. So instead of this sort of toy, the real I/O, in-cats effect, a super library, a great library. It's so useful. It builds on the whole type level ecosystem. It builds on Scala. It provides so much. I can't show all of it, but I'm going to try and give you just sort of the quick cheat sheet of how you might use it. So it's a data type. You can think of it as, one way to think about it if you haven't used it before is everywhere you use future or perhaps try, you could just replace it with I/O and your program will get better because it's safer. So we have to get into I/O. So the most common method that you might use would be the I/O delay. It's alias to just I/O apply. So you can just say I/O parentheses and give it an expression. So this is where the delay happens. You can see that this is a by name parameter. That's what this little arrow means. It means whatever I pass into the I/O factory method there, it's not going to evaluate it. With normal function calls, an expression passed in as an argument to a function is evaluated now before the function's called. With a call by name argument, this little arrow, it says, don't evaluate it now, evaluate it later. And that gives us nice semantics that we want. So this will capture the side effect and produce an I/O that when it's run later, when you unsafe run something, eventually you'll get an A out of it for whatever the expression produces. You might already have a value. But you need to be, you need it to work in sort of the I/O ecosystem. So one way you can lift it would just be through the pure method, and you would give it an already existent value. And that, again, would give you an I/O array. This is more dangerous because you don't want to do a side effect when you call when you pass an argument to pure. That sort of defeats the whole purpose. If you ever perform a side effect, you want to use the IO apply or delay. Pure is just about values that have already been evaluated. These are true values. So that's how we get into IO. There's usually sort of 3 steps. You get in, you do a bunch of stuff within that world, and then you might get out. So once you're in the world, these are sometimes called combinators. They're about transforming the IO into another IO. So these are very familiar things. These would be sort of the most common combinators. You can map, this would be IO A, give you an A to B to an IO B. Map N is the applicative map. So that would take multiple IOs and allow you to combine their results into a single IO. Flat map, or typically you would use it in a for comprehension, that allows you to sequence IO effects. We'll call these things effects now. So an IO value is an effect that produces a value of type A. So flat map lets you execute one IO to produce yet another IO. So they're connected together. And then there's a whole slew of error handling. So if there's an error, there's a notion of error with IO. So you don't see it in the signature. So there's only one type parameter for IO, and it's about the type of the value that produces if that computation is successful. So if I'm successful, I will return an A. But you can imagine some expression that you've captured here that, say, throws an exception. There is a notion of error in IO. So for map, map N, flat map, these would stop. They would not return a new IO if there was a failure. Sort of as would a future, as would a try, any sort of other kind of monad. But we could do things like recovering from errors. So we can handle an error. That would transform the error case. The error case for an IO is a throwable. So we could choose how to handle that throwable. We could produce a new IO. We can produce a value. We can transform that throwable into something else. There's a whole bunch of variations here. But we're still working within IO. So these are sort of IO to IO kinds of methods. So we go into IO. We sort of play around in IO. And then when we're done, usually at the sort of start of our program to start the whole process, most commonly we'll use these. They're all unsafe. These are sometimes called eliminators. We take the IO and we rip it apart. We take an IO and produce the A inside of it. This is run sync, so it's unsafe because whatever we're doing is performing side effects perhaps, and substitution is not involved, so that's a little warning to us. We're running it, and we're running it synchronously. So if we have an IO of A, it's going to produce an A. You can imagine, and you'd be right, that there's a run async, and that would run it asynchronously. There's other options. And sort of as a beginner or someone new to library, and probably it's likely that you're using future in your code, you can convert an IO into a future. So there's like an unsafe to future method. So this is sort of tears that IO apart. So these are the basic steps. There's not much to show about it, but I'll be giving more and more examples. This is how I build it. Now, since it's a really good idea to only to perhaps maybe never call, well, someone's going to have to call that unsafe run at some point. So the smart folks of CatsFX says, well, let's make our own application class. So in Scala, there's the app class that you might typically use, where there would be the main method and things like that. So there's an IO app, and sort of its version of main is this run method that you have to implement. And so the entire program, when you run the program, that is supposed to return an IO. It's an effect. It's some effect that's going to run, and it eventually, it eventually is going to return some execute that says, you know, I succeeded or I failed. And so you can imagine implementing this run method. You return an IO, and you'll remember that IOs, nothing has ever run yet. So that must mean that IO app itself is going to run that IO. So it sort of takes the pressure off. You no longer have to call unsafe run from anywhere. If you implement IO app, you just implement run, return some IO, and it's IO app's job to do, you know, to do the dirty business there. So this would be like an example of a, you know, hello world. I have some hello world effect. It prints hello, it prints world, and the definition of, oh, that's not right. That should be a print line in there. Aha, bugs. Good thing. If we use substitution, you could figure this out. This would, you know, print hello world to the screen. So we're just composing programs. Nothing actually happens yet until we return this IO, and IO app says go. All is well. So I went pretty fast, but there's not many unexpected things. Once you sort of learn to construct IOs, you know, passing in things, and then using sort of normal combinators, normal constructions, you know, using for comprehensions, you just build up larger programs, and then the IO app itself will then run them for you. So that's like the super fast, you know, cheat sheet for IO right there. Okay, so that's fine. You know, I've given everybody more work to do to convert all their code from future to IO. You went through, maybe you wrote a program, maybe you're old school like me and you just did like a sed script and you just changed future to IO everywhere and everything just compiled. We get more from IO. So IO lets us do more. So the next thing we're going to talk about is sort of the real workhorse of it. It's about parallel execution. So when I teach this course, and you know, the course that these slides are based on, and now, you know, when people read the book, part of the difficulty with parallelism, you know, we have these multi-core computers, we're running code in parallel. How do you know that something's running in parallel? You kind of have to actually do a side effect to say, like, you know, and we're running on the JVM, so we're using threads. So you really want to know, am I using these threads, or do I have a single threaded program? So in the examples that I show, I'm going to take advantage of a little extension method that I cooked up. It's just going to be this little debug method. And I have to say, I totally stole it from the FS2 folks, because it's a really nice idea. It's like, I don't know what to do. Just add a debug in there and you're done. So it doesn't have any actual effect on, it sort of decorates an existing IO, and it doesn't change what this IO does, but it just adds a little bit of printing. So it's going to print the current thread name along with the value that was in the IO, and then just yield the value so that normal processing continue. So the idea is that if I'm just trying to figure out the lay of the land, if I'm trying to understand the behavior of parallelism with respect to IO or something like that, I want to be able to see like where my code is running. So I have this little debug helper. So here's a little app, and all it's going to do is it's going to do a map n of two effects. So hello is an effect that's going to debug the value hello, so that will print hello to the console, and world will take this value world and print it to the console as a side effect. The values inside will carry on. So when we compose with map n two effects, we get their output values if they both succeed. So hello would produce this H, and world would produce this W. and I'm creating a new effect out of 2 that's going to produce this new value, collecting them together, and I'm going to debug that. So if I run that program, I can see my, oops, these ones aren't supposed to be there. I see my hello, I see my world, and I see my hello world. So no mysteries there. I'm printing to the console. But the thing to notice is that when I do when these IOs execute and when their composition executes, they're all running on the same thread. They're all running on thread 0. So what I'm intending to demonstrate here is that IO as on its own doesn't have a notion of running things in parallel. It just runs things, sequentially. So there's some other way to access parallelism. And it's pretty easy in some senses. We just add par in front of our map n. Just add par. There you go. Oh, my hand's not appearing. So with a par map n, it's a different method, and it accesses different behavior. So if I have the same program, change map n to par map n, there are a few requirements that need to be there, but if in this example, nothing else needs to change except those three letters and a capitalization. If I run that, I can see with my little debug helpers, because they print out the thread, ignore that little 1, that's my mistake. We can see that hello and world are running on different threads. This is so amazing. And then finally, the combination of them, is running on some other thread. Well, it runs on whatever the last one is, but it's really a detail. So now with a little bit of help in order to see kind of what's going on, we can see, oh, these things are running in different threads, and I can sort of, that means that they're running in parallel. Aha! So what's really nice, and I don't know, it's kind of nice when you just change 3.5 characters, and you just sprinkle on parallelism. It just kind of works. It's really great. So that's kind of like the simple recipe. Oh, and it's also sort of implied in the structure of the computation. When I have these 2 computations, I also notice that world happened before hello. And that's because they're running in different threads. They could get scheduled in any order. So these all just happen. Okay. So we went from map n, which is just sort of a sequential notion. It has at least sequential semantics by default, and we changed it to par map n, and now we have parallel semantics. If you recall error handling in a sequential world, even with an applicative map n, goes, there's some order which it executes in, and it happens to execute left to right, which is a sensible default. But if you're executing this code, here's a little bit more complicated thing. How does error handling work when there's parallelism? So here's 3 effects. There's the OK effect, which has no errors. There's the KO, the opposite of OK. It raises an error. I probably should have mentioned that one, but so just like you can create a successful IO value from just a regular value with pure, you might want to take a failure and lift it into an IO. And so the failure type for an IO is an exception. So you're basically lifting an exception into an IO. You can use the raise error factory method. We say, oh, it would have produced a string, but it actually threw an exception. So KO1 is going to throw an O, and KO2 is going to throw a nose. And we're going to have 3 little test cases. So in all of them, there's an error, there's a KO. So we need to think about what is the value, what do these composed effects evaluate to? we can assume that since there's an error, we're running these in parallel, we're running these in parallel, we're running these in parallel. We know that if any of them have an error, then it's fair to assume that the composed effect will err. And one way you could deduce that would be for parmapn to succeed, it needs to apply this function. This function can only receive arguments if both of its input effects produce values. But we know that KL1 does not produce a value, so essentially the value of this slot would never be produced, which means this function would never be called, which means we can't, we have to produce an error. We can't actually successfully call this function. So we know that all three of these effects here will fail. And one question would be, well, what, and with our little debug helper here, we can say, okay, well, what output do we see? So going through them, here's what you see, you typically see, I should say. It's a bit of an exercise to think about why it might not show exactly what I put up here. But, so we see the output of okay, that was like hi. And then the failure happened. So the failure doesn't produce any output. And then the value, we're getting a debug on the whole effect. And it prints, it says, and if I just back up 1 second, you'll see that in my program, here's my IO app, here's my program. I'm using this combinator here. It's one of the error handling combinators. It's called attempt. And what attempt does is, normally if there was an exception thrown or an error raised for an IO, all execution would stop. There's no value to produce, so you can't keep going. But what's interesting about attempt is it sort of takes an IO of A and will give you an IO of an either. So if there's an error, you'll get a successful left of throwable. And if it succeeded, you'll get a successful IO of right of the value. So it's a way of sort of ensuring this effect succeeds, and the value represents the fact whether the computation, whether an exception was thrown or not. So that I'm using that in order to run all of these effects, which I know to fail. So we see in the end that E1 is a left, and my screen, we get an O. Okay, that's fine. If we reverse these arguments, you'll get something similar. Maybe you'll just see the O. We know that this is the value of E2. It failed. Okay, fine. Okay, didn't have time to run in this example. Maybe we got lucky. And then there's the example, well, what do you have 2 errors? Which error do you get? Well, it's non-deterministic. We don't know. Both of these effects will raise an error. And really, it's just whichever one happens first is the one that the composed effect will become. I don't know the right verb, but we'll assume that value. So it could be that we get an O because KO1 failed first, or maybe KO2 failed first. It's a bit non-deterministic. So that's one caveat to know about. Just as mapn requires all the inputs to succeed in order to produce an output, the same conditions hold for running things in parallel. And because we have to stop, it ends up being whichever error happened, first according to the system. Are people still there? Tell me, Salah.
There are. You got
Okay,
63 people on Twitch right now.
Okay, good to know. Just need to check. So we can par mapn, just sprinkle parallelism. There's a couple other forms that essentially do that launch. You could think of them as running things in parallel. There's the ubiquitous traverse, everyone's favorite method. It's either map, flat map, or a fold, Oh, and most folds are probably just traverses. So there you go. The answer is always traverse. So instead of traverse, we say par traverse, and that will. So the form of a traverse is you typically would have a collection. This is like the work that you want to do, the set of work items. So I made this tasks, and it's just a bunch of ints. And then what else is involved in the traverse? There's a set of things of work, and then there's a function. Here's my function that does one unit of work. So given an int, I'm going to do my I'm going to process it, and my result type happens to also be int. It could be whatever you wanted, and it's just some dummy kind of thing. And so given a bunch of work and a function that produces an effect for one piece of work, the output of traverse would be one effect that has the list of all the outputs. So I traverse over the collection is a typical example. You give it a function which does that work, and then I'm going to print the output. And so I get a bunch of output. And you'll notice that it happens when I par traverse. I get a bunch of different threads. I get threads 1, 2, 3, 4, 5. I have 8 threads available on my JVM. So this lets you do a whole bunch of work. And then the normal cousin, sibling, who knows, maybe sibling, of traverse is sequence. And that's where if you have a list of effects, you turn it into one effect with a list of results. So that's what sequence, and it's a sibling, it's evil twin, I should say, par sequence. So anywhere where you have map, traverse, sequence, you now have access to these par versions. And under the hood, they get scheduled, and they'll run on top of the existing threads as much as they can. That is like the super basics of parallel execution with I/O. Very similar to future, except with future things are a lot more implicit. You implicitly have parallelism. I/O, on the other hand, you have much more explicit parallelism with this different set of combinators, different set of operations that you can do with the par. Okay. Any questions? All right, I'll keep going. How's my time? All right.
Yeah. Not on Twitch. We're all good.
Okay. Okay. So they're kind of two. So that we talked about effects and substitution. We love substitution. We have our I/O, which lets us perform substitution and understand our programs, refactor them. We sort of get this parallelism. We just add parallelism. Oh, life is great. But then it gets a bit more complicated. We start to run everything in parallel. Why not? We have these great computers. Just add more parallelism. Everything's going to get faster and faster. It's going to get ludicrous speed. How much parallelism can we really get? So if I write a little program, I figure out how many CPUs I have in my JVM, and then I do a par traverse, and I give it more work. I give it more work than CPUs. So I'm going to produce twice as much work as I have CPUs. Let's see what happens and sort of debug our results. If I have, what happens? Let's see. Did I even print it? Oh, I was going to switch screens, but I don't think I can switch screens right now. That's okay. Let me tell you what happens. We kind of saw it in the previous par example. My computer and my JVM, they only have so many threads available. And it turns out that I have, on my computer, I have 8 CPUs. And And when I have these little debug statements that sort of say, oh, I'm doing work, what thread am I on? I will see output that says, I'm on thread 0, I'm on thread 1, all the way up to thread 7. So I really don't have access to more than 8 threads. Now, it's not true that a computer can, so one question we could ask is, can a computer do more than, if I have 8 CPUs, can my computer do more than 8 things at a time? And it's kind of a subtle question because we could say, well, obviously, my computer's doing more than, my computer right now is definitely doing more than 8 things at a time. I see UI updates and all sorts, there's network things going on that I don't see, and my I don't know what, but there's lots of things going on. Surely there must be more than 8 things happening at the same time. But it's kind of a matter of what you mean, because I only have 8 CPUs, so really only 8 CPUs could be doing something. So what does it mean to have something happening? And so kind of what I'm trying to lead you towards is the idea that there's some sort of abstraction going on here. And the idea of a thread, for example, we could just program directly against some super low interface that says, you run this I/O, for example, on a CPU, and you have to give it the CPU that you want it to run on. I want to run it on CPU 4. And then if something else tries to run on CPU 4, well, it would have to wait till it's done. So, the elders in our field said, well, this is silly. I don't want to have to say what CPU I want to use. I'm going to just make this, I'm going to abstract over the number of CPUs. And so I'm going to have sort of this logical notion of computation, and we'll call it a thread. I'm making up this history, but this is one way to kind of summarize it. And you can have as many threads as we allow. And so you as a programmer can think in terms of threads. And those threads will all sort of compete for the use of those underlying CPUs. So you don't have to think about CPUs anymore. You have to think about threads. Okay, that's good. But how do those threads, who says how those threads, use that underlying CPU? And, it's the JVM's job to do that. Oh, okay. And there's some rules in there, and so on and so on. But essentially, we have this layer of these layers of abstractions that let us have access to certain concepts, and certain concepts are hidden. So the idea is that whenever we represent some computation, if we have an I/O, for example, and we're doing a, say, PAR traverse, this is also an abstraction. A simple way to think about it would be that all of these tasks, when I run this traverse, I get back 1 I/O. And when I run that 1 I/O, there's going to be, in my case, 16 tasks that are all trying to compete for those 8, 8 CPUs, say. Whose job is it to make that assignment? Well, we'll see. So this is kind of the dilemma. If I have 16 computations and 8 sort of threads, you might say, how do they fight? Well, they can try and be. You could assume that all of the computations are fair. If all of the work was doing some very short amount of work, we could be like, okay, I don't have to worry about them. It's going to be sort of non-deterministic, who wins, but they're only going to use that thread or that CPU for a very short time, so it doesn't really matter. The problem comes when it's like my kids, they're fighting over the Legos. There's only so many Legos. They have to fight over them. So what if nobody gives that CPU back? What if somebody's hogging the thread? Well, now there's less threads available, and we can't do as much work. So that's sort of the normal problem. So we need to start thinking about how do we share this resource? And one concept that we can use is the idea of an asynchronous boundary. So here we go. So we have these IOs, we have these effects. We don't know what they are. We don't know what their code is, right? We've wrapped up something in a box, and we said this is an IO, and I don't know what it does, but eventually it's going to return a string, or eventually it's going to return a unit. I don't know. And maybe that IO is made up of other IOs sequenced together, in a for comprehension. Or maybe that IO is actually the par traverse of a bunch of other stuff, and there's a gazillion little IOs in there. How do they all actually get scheduled so it's a bit more fair? The idea in Cat's Effect and in other sort of foundational libraries is that somewhere there's going to be this boundary, and in a particular one that you could perhaps call yourself is this shift method, and it basically says it's like you can think about it as like I tend to think about it as a hint. It's a hint to the runtime. To the outside world, shift doesn't do anything. It just returns a unit. But to the runtime that actually is running the effects, it says, hey, you might want to let somebody else do some work. And it sort of, one effect that it has here is that it sort of reschedules the rest of the computation to run on some other thread. So if there were a whole bunch of work that somebody did a par traverse or a par map in, there's a bazillion IOs, they're all fighting. These little asynchronous boundaries are a way that sort of makes everybody, allows everyone to make progress. It says, maybe you need to take a little break. The rest of whatever you're doing will happen. It just sort of goes back to the end of the line. And that gives all the other work a chance to continue and make progress. So it's a bit of, in some senses, it's a bit of an implementation detail, but it's a really important one, because if you are programming some sort of loop that is doing all these things, you might want to say, okay, now's a good time. It's not so critical. Let somebody else use the underlying resources and I'll get back to what I'm doing. If you ever have you can think about how you would make a loop in the world of IO. It can be really aggressive. If you just put a while loop, if you constructed an IO with a while loop, it's just going to eat the CPU. So you need to be able to say, whoa, I'm cool. I'll come back later, where later is like, a millisecond. So don't worry about it. So when we have lots of things that, when we have this abstraction of the effect, and we have so many, we can now sort of declare that they're running in parallel, we have to have a notion of, we want our apps to make progress. And sometimes we need to sort of categorize what our IOs are doing. We might have a very CPU expensive IO that we could use the idea of an asynchronous boundary to sort of say, okay, I've reached a good point, maybe let somebody else have a turn, please share with your sister. But there are other kinds of calls. The dreaded blocking, what if blocking is so much slower, that, it's so much slower, we give it a new name. We're not just computing the digits of pi, we're talking to the file system, we're talking to somebody over in the next continent, a network packet happens, we're waiting for a response. Those are much, much slower. So if I had an IO that represents some blocking thing that is 1,000 or 1,000,000 or 1,000,000,000 times slower than some CPU operation, I want to say, I want to like put it off somewhere else, so my application, who might be doing something more important, can use my underlying resources of my threads of my CPUs. So luckily Daniel's here. I stole this quote from him. He actually said it. So how do you know if something blocks? And a good heuristic is if something doesn't have a callback API, then you know it's blocking. So if you see something that does have a callback API, so callback API would be like on complete on error. That means you're registering something for something that's, you're going to get stuck handling. So that's one heuristic. So if you have something blocking, you're reading from the file system, you're making a network call, you're talking to the OS, you're talking to a Java API, we need a different strategy. And in Cats Effect 2, this changes in Cats Effect 3, so put on your Cats Effect 2 goggles. There's just a bit more of an abstraction. So instead of creating just any old I/O, we sort of decorate that I/O using what's called a blocker. And we basically say, we sort of mark, we give it an effect as an argument, and the blocker says, oh, the I/O that we're giving it is really is doing something blocking. And it's sort of, we can look at the code and say, aha, whatever the argument is to the blocker, that thing is going to be blocking. So it gets marked as special, and it's going to be running on a different set of threads. That way, those IOs that are not doing blocking work can continue. They can still be like, aha, I have access to the thread. Yes, yes, I can do my work. And only when that blocking, when that separate pool of blocking threads gets woken up, then work can then get continued back onto the main thread pool where everything else runs. So here's a little program which demonstrates kind of how Blocker works. And we have a regular I/O that sort of is non-blocking, or doesn't involve blocking. Is probably the better way to say it. We sort of mark this other effect as, oh, this is going to do some blocking work. We're calling a Java API. Beware. We're going to push it over somewhere else. And then some other effect that's going to run after the blocking effect finishes. So we see that we're on this. What thread are we on? We're on the IO app. IO app's default thing. And then we can see that the blocker is on a completely separate thread. These are managed totally separate. So now blocking work does not interfere with regular good old IO CPU oriented work. And then after the fact, we're back. So you'll see these, in your code, in your libraries, you'll see these blockers being passed around in Cats Effect 2. In Cats Effect 3, there's essentially a constructor for creating blocking IO. So it would be like IO.blocking, and you declare at that very initial point that whatever the parameter is, I am blocking. You don't have to have a separate blocker, which is nice. There's less concepts involved. So now there's sort of two big contexts in the world. There's different ways to slice it. We can launch all this stuff. We have parallelism now. Once you start to take advantage of that parallelism, there's sort of different flavors of work. There's and the dangerous flavor that you need to be aware of are those blocking tasks, things that don't take nanoseconds, but take milliseconds or even seconds to complete. We want to push those into a different sort of section of the world, and we do that via this blocking context. And then sort of behind the scenes, to ensure that the work that we have scheduled makes progress, there's this idea of an asynchronous boundary. They happen automatically a lot in Cats Effect, so you don't have to explicitly put them in, but we can put them into our computations, into our declarations of effects, so that they can proceed. All right, so that's context. We had parallelism. We have some, if you have so much parallelism, you got to start partitioning your work. Sort of zooming out a little bit more, more at the level of how do we organize our applications. I'm going to talk briefly about managing resources, and then I'm going to finish up. So what's a resource? So I asked the question to sort of motivate the there's a corresponding abstraction inside of cat's effect. So the idea of a resource is that, well, we can think about it. It's something that has some state, perhaps, and it's somewhat expensive. We want to keep it around. So usually I would say the classic example of a resource would be like a file handle. So when we deal with files, the usual API is we would open the file. That would sort of produce some sort of handle or file object. We then use it, we read to it or read from it or write to it and so on. And then when we're done with it, we have to close it. So, this is especially important if you're writing to it. Once you close the file, you can't write to it anymore. Or if you try to, it should be an error. If you, in the old days, you could actually, it's still pretty easy, but you might forget to close the file. So maybe when you're writing, you're actually just buffering things into memory and not, when you close the file, you're sort of that final commit that ensures that those bytes get written to whatever IO interface. So a resource is sort of the idea of, well, not only are we trying to do something like write to a file, but there's some state that we need to manage. There's a step that sort of says, okay, this is how I acquire my resource, like a file handle. I can then use it. And then finally, I have to release that resource, just like memory. I acquire a block of memory, I use it, I do whatever I want with it, and then I free it. That pattern happens over and over again. So in cat's effect, we have an abstraction for this. And so it's called a resource. And the way you build one, so the job of the resource is to sort of separate that the acquire and the release step, sort of capture those right now. I know how to create a file handle, and I know how to produce a file handle, and I know how to close the file. I'm going to capture that logic into a different kind of abstraction, and we're going to call it a resource. So a thing to notice here is it takes two effects as arguments. I'm going to have an effect which produces, sort of the underlying resource. This produces an A. A would be like my file. And release is a function which produces an effect. It takes the resource, my file, and then produces some effect. So this would be the closing of it. And then you get a resource out. So I'm not in IO anymore. I get a resource. So here's a very toy example. I'll start here. I have a very important string. This is my resource, and it's involved in IO. So when I acquire the string, I'm just going to produce some string, and I print some little debug information beforehand. So I'm acquiring it, and when I'm releasing my string, I just say, hey, I'm releasing it. So I've captured the acquisition, I've captured the release. What can I do with a resource? The important part of a resource is using it. So when you use a resource, you get the acquired value. You give it a function which produces some effect. So in this case, I get a value of type string because my resource is managing a string. I get my string and I can do whatever I want with it. But once the effect that I return, when I use it, my job is to produce effect with the value of the resource. Once my effect is complete, then essentially here after this effect runs, that's when release happens. So you get this bracketing effect. So in sort of the debug output, I acquire it, it gets used, and then it gets released. So that pattern, we have it all over the place. So you can imagine creating resources where the resource value is a file, is a database connection. You acquire a database connection, you use it, you run it with some SQL or whatever, and then you're done with it, and the connection goes back into the pool or it gets free or whatever. All those patterns that are a lot more implicit in your code become much more explicit. You make a resource and define how you get it and clean it up. And somewhere else, usually, often in the top level of your application is where you have resource, or maybe, you often have more than one, and you use them. And this is like your business logic. This is a dependency. This is dependency management in Cat's effect. I have a dependency. I say how to make it. I say how to clean it up if it needs cleaning up. And it's someone else's job to use that dependency. But it's guaranteed that when you use it, it gets properly created, used, and then released in the proper order. So it's very handy for all sorts of things, both ephemerally and sort of at a top level of your program. You define your database connections, anything that sort of needs set up and tear down, you can always model as a resource. It's super handy. I didn't have time to do all these things, but here's a couple examples. We talked about file handle. There's a really cool method you should check out on I/O. It's called background. It essentially would fork your I/O to run on its own. You sort of detach from it, but it's running. But you get a resource that represents the lifetime of that fiber, of that effect. So say you had an effect which just sort of keeps on doing stuff, a clock, a certain sort of reactive loop. You could then shut down, the resource represents the lifetime of that background task. Another thing to note is we can compose resources. So I just had an example of one resource, but if you had two resources, you can map resources, you can flat map resources, you can map n resources, but you can also par map n or par traverse. You can essentially par map n resources. So that would acquire resources in parallel, and then their release would happen in parallel also. So it's a super handy structure that's intimately involved with I/O and effects that captures a very common pattern. Okay, so that's all I have. There's really a lot more. Let me go quickly summarize. So we started out talking about effects, and I wanted to really emphasize again, because we should all have this internalized. Like, substitution is super important because it gives us so much. It's the gift that keeps on giving. If we delay the execution of these side effects, and if composition allows us to be referentially transparent, we can build up our programs and refactor them, and nothing will change. We won't introduce any bugs by refactoring. That is a great thing that we have access to. So if we want that, we can use Cat's effect I/O. We capture these side effects that are dangerous, that don't support substitution. They get this nice, safe interface. We compose, we do maps, we do flat maps, we do map ends. And only in the beginning of our programs do we say unsafe run. Or we even use IO app to not even have to say that. We just declare what our program should do, and it's the system's job to actually do it for us. We're not responsible for those side effects. We've properly wrapped them up. We get parallel execution. We sort of sprinkle our pars in. We can par map, par traverse, par sequence, par tuple. Forgot about that one. That's a good one. Now we can run many things that are independent, and we can take advantage of them, take advantage of the resources that we have on these big fat machines that we have. We can use them for their, what they really can do for us. But once we start trying to do more and more things in parallel, we're going to run into the actual limitations of how many CPUs we have, how many threads we have. If we have threads, we don't want to block on them because we could be interrupting other people's work. So there are a couple of concepts involved there. We have this asynchronous boundary, which says, okay, I've done enough work. Maybe it's time for someone else to do the work. And also we have sort of the notion of categorizing our effects as blocking or non-blocking, and those will use separate set of resources so that everything keeps chugging along, that we don't sort of starve ourselves. There's a very common pattern of acquire, use, and release, and sort of the resource data type in Cat's effect lets us encapsulate that. Very useful for dependency lifecycle management. And there's like so much more. There's the notion of fibers, which we didn't get to, other ways of building asynchronous computations. There's a whole bunch of concurrency primitives for sharing state, for doing semantic blocking. You'll get to learn what that is later. But that's, I think, a good amount to throw at you there. Hopefully this makes you excited if you haven't seen it before. It makes you excited to change little by little your applications, your business logic, the libraries you use. There's a huge ecosystem. Here's a super brief list of places you can go next. There's always the Cat's Effect website. I learned all the tricks from these great folks who are online, especially this Gitter room. You have a question, people are going to help you. They'd love to help you. And then, I saw that people had lots of questions about Cat's Effect. So, there's some great blog posts out there. And so my current project has been to produce this book. So it's available now for early access. You can check it out, essentialeffects.dev. I think it's a reasonable price for what you get. It's like 170 pages. Let me know if you have any questions about this material. I'll post my slides. Ping me on Twitter anytime. I'm a Rosien. You can hire us, Inner Product. If you need help migrating to Cat's Effect, no problem. Training your staff, whatever kind of side projects, we can help you out. So I'll leave it at that. If there's any questions, and hopefully there's also the deep experts are also online to answer any extra special questions that I may feel too tired to answer.
Great, thank you, Adam, for a great talk. Any questions? Anyone on Twitch, anywhere on here on Zoom? There's been a few questions on Twitch, but I think Daniel's handled those. Other than someone asking for a question related to comparing Cat's Effect 3 and Zio. I don't know, Daniel, whether you want to expand on it today or what?
Yeah, I can expand on it a bit if there's interest in it. I think the TLDR for me on comparing Zio and Cat's Effect is that it's difficult to compare them together one-to-one. Cat's Effect is a library. Cats is a library. Zio is a framework. And I use those words to kind of evoke the old spring versus juice idea, some of the stuff that those of us who've been unfortunately around in the Java ecosystem, from those days might remember some of that. Another one you might think about as a metaphor here is if you think about play versus like a Sinatra style library for doing REST routes. That type of distinction is what it is. Now, again, there's no disparagement in that comparison, right? Play is a fine framework, Spring is a fine framework. People write applications in Spring today, and they choose to do that for a good reason. And the reason that you choose to write in terms of a prescriptive framework is the choices are made for you. When you want to do something, there's a right way that it will sort of guide you down. If you want to do dependency injection, you're going to use ZLayer. If you want to do sort of, error handling, you're going to do it in this way. All those sorts of things, Zio has answers for, and it will sort of guide you in that direction. And especially for beginners, that can be a very appealing path. The type level ecosystem, conversely, is designed to be a composable set of libraries. So what that means is that it can be at times a little bit less batteries included. Like, you sort of have to make some choices as to, how you want to compose things. And that can be a bit daunting. I think there's ways that has to be improved. And, I definitely feel like we can own that. But the advantage to it is that you will never hit a point where the library can't go with you any further. Like the classic problem with frameworks is like, as long as you're in the happy path of the framework, the cases that they considered really well, the framework is going to be awesome. And you're going to have a magnificent experience. It's going to be just completely unparalleled and really, really nice. And then there'll be a moment where you hit a wall and you're just a little bit outside what the framework, your problem space is just a little bit outside what the framework considered. And you can't really do anything. Like you're sort of stuck and you have to fight the framework from that point forward. This is a problem with Spring. It's a problem with Play. It's a problem with Akka sometimes. And it's definitely a problem with Zio. Like you will hit that wall at some point. And you might hit it in different ways, right? Like a classic example is like, notches, doing tracing, distributed tracing and threading spans to your application. Notches is a great library for doing that, but composing it with Zio while you can do it, it's a little bit weird. Like it's kind of like this thing off on the side. It doesn't use the normal environment. There's other more elaborate examples that you can come up with. Whereas like in the type level ecosystem, all of those examples just sort of layer on compositionally. So I think of it in kind of the old, Eric S. Raymond metaphor of the cathedral versus the bazaar, right? Like the Zio ecosystem is very much a cathedral. It's very curated, sort of like, this set, everything kind of fits together in exactly this prescribed way. The type level ecosystem is a little bit more like a bazaar. You can kind of mix and match. Things compose together. You can build arbitrarily complicated things, but it can be a little difficult to find your way. So I see the best way to kind of bridge the gap between these and provide a really compelling experience for newcomers and experienced users alike. Obviously within the type level ecosystem, because that's where I'm biased, is like, okay, I want to give you the bazaar so that you have choices, but I want to give you a nice map to that bazaar. I want the bazaar to be really well organized. And I want you to have a really good experience. When you walk into that bazaar, I want you to know, okay, you're looking for shoes. Here's some really nice shoes. Like the metaphor is getting a bit stretched.